Okay, we are almost there. Kirchoff's laws are a great bit of fun, and then we'll talk about potential dividers, and then I believe that is it. So just two more topics. Right, Kirchoff's laws. There's two of them. One's about current, one's about voltage. The one about current, I think, is actually pretty common sense, but it's worth always bearing in mind when you find yourself facing a complicated circuit. It's a lifesaver. Okay, so when we're running an electric circuit, we're not getting rid of any electrons. You can't create and destroy them. And just like a system of water pipes, we're not getting rid of any water molecules unless there's a leak, which there isn't really a comparison for in an electrical circuit. If I have a junction in my circuit, all the electrons going into it have to equal the electrons coming out of it. That is Kirchoff's law, essentially. It's just conservation of charge in application. So for any point in an electrical circuit, any junction, the sum of current flowing in is equal to the sum of current flowing out. So if I label these currents, we've got I1, I2, I3, I4, and I5. We're saying that Kirchoff's current law applied to this circumstance would say I1 plus I2 is I3 plus I4 plus I5. Simple as that. The sum, this big, for those of you not familiar, this big, I'm forgetting the Greek letter, but that means the sum of all the currents going into the junction, into the node, is equal to the sum of all the currents coming out. Kirchoff's second law, or Kirchoff's voltage law, is a little more subtle, a little harder to derive, perhaps. It says that for any complete loop around a circuit, the sum of the EMFs around the loop is equal to the sum of potential drops around the loop. For the loop on the left, this is easy enough. You're saying, well, look, I start here, and as I walk around, I gain 9 volts. That is an EMF. I'm gaining some EMF, and then, oh dear, I spend some potential drops. I spend 6 volts here, therefore I must spend 3 volts here. Okay, so it's pretty simple when it applies to just one loop. So the sum of voltages is the sum of EMF, and they're both equal to 9 volts. The picture can then get a little more funky, and we will see an example of that when we get to the exam question. But let's turn our attention to this picture here. It says for any complete loop, so we can actually apply this to this tiny little loop here. And for this tiny little loop, it's actually fairly self-evident. We know that the potential difference between this point and this point is a constant, and therefore it cannot depend on which path the electrons go down. They will spend equal number of volts regardless of the path. So if you go around this path, you start here, you say, oh, well, the current is flowing this direction, let's say. If I start here, I say, oh, look, I lose some volts. It must be 2 volts because I lose 2 volts up there. I go around. I'm now going through this component backwards. So in a sense, I'm gaining 2 volts. 2 volts, 2 volts. Let's think about the big loop here. Let's start our journey here. I go through these 2 cells, and I go through them the correct way round, and I gain 24 volts. Fab. I then go through this component, and I lose 2 volts. There's 2 volts spent there. I then go through this, and I lose some more volts. I don't know what that is yet. I go through these two cells, but I go through them backwards, which also has the effect of depleting some of my energy. So I have 24 minus 12. How annoying is that? Mathematically, it has the same effect as if I'd gone through a resistor expending 12 volts, but it's technically counted as an EMF rather than a voltage. Not that that really matters because we can chuck them either side of this equation anyway. Okay, let's do a little bit of simplification. 12 equals 2 plus a mystery number. You don't have to be a genius to realize that that is 10, therefore. Okay. Right, let's apply this to a slightly more complicated diagram. Consider the following circuit diagram. Current flow D is 3 amps. Kirchoff's laws determine the current flowing through resistors A, B, and C. It's 4 marks. Oof, okay. Right, we have a slightly complicated circuit here. So let's consider the bottom right closed loop, where we don't have much time, so I'm going to have to push through this, which is a real shame. We gain 20 volts here, we expend some here and expend some here, and we're told the current through here is 3 amps, that resistance is 4, so we know this is 12 volts. Multiply those two together. V equals IR. Therefore, the voltage here must be 8, because 12 plus 8 is going to have to equal 20. Great. If the voltage here is 8, this is 2, that means I2 is going to equal 4 amps. Great. If we've got 4 amps going into this node, 3 amps going this way, that means I3 is going to be 1 amp. Conservation of current. If this is 1 amp going through here, then the voltage across it is 3 volts. Consider this loop down here. So we're going the wrong way through this, so we're losing V volts. We're then going the wrong way through a resistor, so we're gaining 12 volts. And we're going the right way through a resistor, so we're losing 3 volts. So we've got minus V plus 12 minus 3 volts. So, and that's got to equal 0. So therefore V is going to be 9. Okie dokie, and last but not least, we can say we can take the loop as a whole, this huge loop. You gain 20 volts here, you lose something here, you lose 9 volts here, and that's the end of the story. So you're going to have to lose 11 volts here. Therefore, I1 is actually 11 amps, which is a huge current. Okay, hopefully that's correct. So that's done very quickly. I2 was in fact 4 amps. Hooray, congratulations. Where was I4? Yeah, 11 amps for I1, 1 amp for I3, and V was